In Lesson 75, Paul led us through the hardware and software installation of the infrared remote control and sensor. Our Lesson 75 assignment was to create a program that would compile a list of IR remote button presses and display them in the shell. The goal was to start recording key presses when the power button was pushed. Subsequent key presses were then to be recorded until the EQ button was pushed, at which point the entire command string would be displayed in the shell. Also, key codes of -1, signifying a repeated key, were to be ignored. Our Lesson 76 assignment was to use the IR remote to set the position of the servo motor between 0 and 180 degrees. Our Lesson 77 assignment was to use the IR remote to display some bodacious patterns on the NeoPixel strip. And finally, our Lesson 78 assignment was to add an SSD 1306 OLED to our setup and redirect status messages and user prompts to the OLED. I balked at the idea of manually sorting out which key code corresponded to which IR remote button. So before working on the actual assignments, I created a program that would add, change, delete key code button label pairs and save them in a JSON file on the Pico W. I freely admit that I replaced what might have been 20 minutes of manual work with a couple of hours of programming, but I learned a few things. Key learnings from this work were the dictionary get, pop, and item methods. Dictionary name.get of key code returns true if key code is in the dictionary. Dictionary name.pop of key code removes the key code pair from the dictionary, and dictionary name.items returns an iterable list containing all the pairs in the dictionary. The IR dictionary variable is organized as key code button label pairs as shown here. The dictionary editor saves the dictionary as a JSON file. I was reminded that all the entries in a JSON file must be strings. However, our key codes need to be ints. So after reading them from the Pico W file into the IR dictionary variable, we have to convert all the keys in IR dictionary into ints. After a little research, I came across this very compact syntax. Before we look at the assignments, let's have a quick look at the code for the dictionary editor. We start by importing the BK's LED class. Then we import UJSON because we'll be saving the dictionary as a JSON file, and OS because we'll be using the remove file function. We import pin because we'll be attaching the IR sensor, and finally we import the IR routines from the SunFounder library. Here we declare the GPIO pins for the red LED and the IR sensor. Lines 18 and 19 create the LED and IR sensor objects. Next, we declare initial values for the variables used in the callback function and elsewhere in the program. Here we define the callback function, which is called by the SunFounder infrared routines. Whenever a remote button is pressed, the IR routines call the callback function, passing data from sensor and two other variables to the function. Data from sensor will be either a unique key code for the button being pressed or a -1 indicating that the previous button is repeating. If it's not a repeating key code, we assign data from sensor to the key code variable and turn the red LED on as a visual confirmation of the button press. After a brief pause, we turn the red LED off. This all happens without any impact on the operation of our code. We initialize the IR object on line 36. Dictionary file path holds the path to the JSON file where the key code button label dictionary is stored. Here we try to read the file. If the file exists, we load it into the IR dictionary variable. We convert all the keys in IR dictionary from strings to ints in line 41, then print the dictionary in the shell and message the user. If the file does not exist, we message the user and set the IR dictionary variable to empty. The try clause at line 48 will add, change, or delete key code button label pairs in the IR dictionary. In a while true loop, the user is asked if they want to add, change, or delete a button, or press Ctrl+C to close the program. If adding, changing a button, the user is asked to enter the label of the button in question, then asked to press the button. When the key code is received, the dictionary is updated with the key code button label pair. If deleting a button, the user is asked to press the button in question. In line 69, the get method is used to verify that the requested button is in the dictionary, and if so, it is removed using the pop method. The dictionary has been modified variable tracks changes to IR dictionary. When the user presses Ctrl+C, the accept clause on line 77 either updates or removes the JSON dictionary file as required, closes the IR object, turns off the red LED, and exits gracefully. And here's how it works. If the IR dictionary file exists, the number of key code and button label pairs is displayed in the shell. In this case, there is no file, so a no dictionary message is displayed. The user is then asked to add, change, or delete a button pair, or press Ctrl+C. When adding a button, the user is asked to provide a label for the button, then press it. When deleting a button, the user is simply asked to press the button in question. If the button is in the IR dictionary, it is deleted. Otherwise, an error message is provided. Pressing Ctrl+C at any point provides a count of the number of buttons on file, saves or deletes the dictionary file on the Pico W as appropriate, and exits gracefully. Now that we have an easy way to manage the dictionary and store it on the Pico W, we can create a program that reacts to button presses, displays the command string, controls the servo, controls the NeoPixel strip, and displays the program status on the SSD 1306. In addition to the power and EQ buttons, this program uses the mode button to switch the program between servo and NeoPixel control. Here's the code for those assignments. We start by importing the BK's LED and BK's servos classes. We import pin because we're attaching the IR sensor, and I2C because we're using the SSD 1306 OLED. We also import the SSD 1306_I2C library. We import time because we're going to be using sleep. We import the NeoPixel library because we're going to be using the NeoPixel strip. We import UJSON because we'll be reading the dictionary file from the Pico W. And finally, we import the IR routines from the SunFounder library. Here we declare the GPIO pins that we'll be using for the NeoPixel, the OLED, the red LED, the servo, and the IR sensor. Here we declare the red LED, the servo, and the IR sensor objects. Next, we create a colors variable containing a variety of RGB tuples. Here we define a variety of variables used throughout the program. Here we define the callback function, which is called by the SunFounder routines, much as we did in the dictionary editor code. Whenever a remote button is pressed, the IR routines call the callback function, passing data from sensor and two other variables to the function. Data from sensor will be either a unique key code for the button being pressed, or a -1 indicating that the previous button is repeating. If it is not a repeating key code, we assign data from sensor to the key code variable and turn the red LED on as a visual confirmation of the button press. After a brief pause, we turn the red LED off. This all happens without any impact at all on the operation of our code. The IR object is created on line 73. The HSV to RGB function converts HSV or color wheel values into the RGB values required by the LEDs in this project. I won't bog down this lesson by explaining how this code works. The code is explained in my lesson 52, 53, 54 homework. Follow the link in the description below if you want to see that explanation. We configure the OLED display in lines 116 to 119. Lines 124 and 125 define the NeoPixel display and create the NeoPixel object Pix. Line 127 clears the OLED display, and much as we did in the dictionary editor, lines 128 to 147 read the IR dictionary file from the Pico W if it exists. Program status is displayed on the OLED. The progress bar is really just there to delay the program long enough for the user to read the OLED. Here we clear the OLED and display the starting prompts. The main part of the program starts with a try except clause, which will help us exit gracefully. The try clause includes the expected while true loop, which opens with another while loop that waits for the user to press a remote push button. Once a button is pushed, we test that it is in the dictionary with the get method. Now the program operates in one of two modes, servo mode or NeoPixel mode. The mode button changes modes. If the mode button is pressed, the program sets the record commands variable to false, cancels any command string that might be in progress, resets the key code variable, and switches modes. The OLED is updated as appropriate. If the power button is pressed, record commands is set to true, power is appended to command string, and the key code is set to 0. The lower part of the OLED display is cleared and user prompts are displayed. If the EQ button is pressed and command string has at least two elements, we reset record commands, append EQ to the command string, and print command string in the shell. Then, if mode is servo, we extract the servo angle from the command string and move the servo to that angle and update the OLED messages. If mode is NeoPixel, we extract the pattern from the command string, check that it's a valid number, update the OLED, and display the pattern on the NeoPixel strip. The various NeoPixel patterns are basically the same as those used in my homework for lessons 52, 53, and 54. The link is in the description below. With the exception that we break the for and while loops if the user presses a key on the remote control. For example, line 249 captures a key press that occurs while that for loop is executing. The interrupting key code variable keeps track of which button caused the break so that we can actually react to it on our next pass through the loop. Here we can see that patterns 2 and 3 can also be interrupted by remote button presses. Notice that it's often necessary to dig yourself out of nested loops. At line 303, we can see the OLED messaging related to invalid pattern numbers. For buttons that are not mode, power, or EQ, line 312 appends those new dictionary button labels to command string if record commands is true. The message block starting at line 314 alerts the user if they press an undefined button. Finally, we set the key code variable to interrupting key code so that we can respond to it on the next pass through the loop. If the user presses Ctrl-C at any point, execution leaves the main loop, moving to line 324, where we print a closing message for the user, close the IR object, turn all the LEDs off, and clear the OLED. And here's how it works. The program starts by reporting the size of IR dictionary, in our case 21 keys. It then enters servo mode. The user then enters their keystrokes. When they enter EQ, the command string variable is printed in the shell, and the servo moves to the specified angle. Pressing the Mode button changes the program to NeoPixel mode. The command string variable will now be interpreted as NeoPixel pattern numbers. Pressing Mode again will return the program to servo mode. The user sends the servo back to 0 degrees and presses Ctrl-C to exit the program. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.